Good afternoon, everyone. Welcome back to our seminar series, the Mobilise-D webinar set of webinars. You can see here the announcement for the new sessions that have been added to the plan. So if you enjoyed what you've listened to so far, please register also for the two events that we've now planned for May 4th and June 1st. Where we'll be talking about the next part of the study, so the clinical validation study, and then how we are working to make sure that we always keep patients in the center when developing our digital mobility outcomes. So let's come into today's webinar. First of all, welcome back again. I'm Claudia Mazzano, a professor in biomechanics at the Institute of Pharmaceutical Medicine at the University of Sheffield. And as part of Mobilise-D, I'm in charge of leading the work that we have done for what concerns the technical development. Mobilise-D, as you might now have heard many times, but if any of you is new to this series, is a very large project that started in April of 2019. So we have just finished our third year of activities. It's a very large initiative co-funded by H2020 and the European Federation of Pharmaceutical Industries. We have 34 partners that provide multidisciplinary expertise that is needed to achieve our outcome, which is that of connecting the digital mobility assessment to clinical outcomes for regulatory and clinical endorsement. And it's a project that entails a number of partners, both from academia and industry, who are co-led by Professor Rochester from the University of Newcastle and Dr. Rubenoff from Novartis. Just a disclaimer to start with, this is a project that has been funded by the bodies that I've mentioned before, and none of them is, of course, all the opinions that you will hear from me and from all the presentations today do not reflect the authors, the sponsor's view, but only our views. And the second disclaimer that I would like to make today is that of having a very non-diverse panel today, made only by Mediterranean women in science, which I'm really proud of. So apologies for all the men that for once were left out. So in the first seminar of our series, we have been introducing all the algorithms that we have been developing and implementing in order to calculate all of our DMOs and the different blocks that we had to identify in order to get to the estimate of our primary outcome, which is real-world walking speed. And today, what you will be hearing from Encarna is which algorithms best performed when we in each of these blocks when applied to our patient data recorded in the real world. We also showed in session 2, which are the experimental tools that we are using in order to make this validation of the algorithms. And you will hear in particular today from Francesca about the results that we obtained when using our reference system, the Indeep, and how well this system performed when tested on our specific patients before we took it out in the real world. Still, as part of the experimental tools in the session 2, we have also been presenting the way we are approaching our evaluation of the different devices that might be used in the context of measuring mobility, starting from one sensor located at the located on the pelvis. And we have always stressed the concept of how, if we provided that our devices satisfy some minimum requirements, we really want to develop tools and approaches that are completely devices agnostic. And this is Tekla today will be showing you the results of the comparison that we obtained when running our algorithms on different devices. In session 3, we presented all the experimental protocol that we performed in order to validate our algorithms in all different contexts. And Silvia today will be giving you some insights on how well the algorithms performed. In session 4, we have been showing you all the data standardization, how we ran our algorithm, how we implemented them on the science, and how we we have developed a dedicated statistical analysis plan, and how we are planning to share our data at the end of the study. And the way we concluded that session was by really highlighting the need, when we have such complex data and such a number of algorithms, the need for a tool to visualize the data and make them readily explorable in order to make sure that the results we provide are of high quality. And Alma Cantu today will be presenting this tool. So without any further ado, I would like to leave the stage to Alma in order to present her work.
Yeah, so sorry, I misclicked. So hello everyone. So I'm Alma Cantu. I'm going to present so the tool we use to conduct the analysis. But first of all, I'm going to say a few words of how we designed it. So we rely on an interactive process centered on users. Which first start by identifying users' needs, then we develop prototypes, then we evaluate prototype we develop, and we keep iterating through these different steps to provide the final result I'm going to present today. So what's the user need identification? Is first identify who as a user. So it's going to be researchers and scientists analyzing mobility data. So mainly everyone that present this webinar so far. The needed context is we were looking for a tool to validate technical assessment and to identify all this need. We've done a lot of brainstorming with everyone. Then we first implement prototype. We investigate existing work in visualization and biomechanics. We try different techniques on the data, and we build a portable solution so we can share it among the consortium. And then we evaluate it by coming back to the user, so with the research and scientist analysis. And we try to get as measures as objective as possible, like interaction time and number of viewers. So before presenting the tool, I'm going to quickly say a few words about the data we're going to see. So the idea was to go through the different DMOs, that stand for digital mobility outcomes, which are several. And for all of these DMOs, we wanted to access which algorithm would be the most suitable. So for this, for each algorithm, we compare the reference system, so the results we got from several sensors, to the result of the algorithm applied to a single sensor. So it's what we call RS and SS, or SU, that's for single units. We're also interested about the absolute error between these two results and the relative errors and many more metrics. And we apply all of this to a lot of different information we had, mainly measurements that come from different cohorts, but also different sites and several participants. So this is what to look like. So the main bit is this part, which is close to what we call a parallel coordinate in visualization. So each line represents a measurement, and the line goes to the different axes according to its value. So here we found back the cadence value from the reference system, here from the single sensor. And all these lines are emerged into ribbons according to the categories they belong. So like different cohort, for example. So measurements represented by lines and grouping ribbons. And here we have cohort access, algorithm, type of test, type of walking bout. So if it's a short walking bout, less than 10 seconds, medium 30 to 60, and so on. Cadence RS, as I was saying before, cadence is single sensor, absolute error, and relative error. This tool also allows us to add all the different variables that are contained in the file, because we cannot display all at once. We also have here a summary of the display data. So just the quantitative axis we have here, we can find them here. So cadence RS, SU, absolute error, and relative error. We have the mean value and the sorry, I just forgot the word suddenly. The confidence interval, sorry. This will also allow us to have here a correlation and a blind map plots that are displayed on demand. So basically we can select different axes here, and we can decide which axis we want to be displayed on the correlation and blind map plot. We can also decide to click on a specific datum, and we have here all the detail of this specific single datum. And finally, we have here legend that describe the different color that's are used to color the view. So if you keep your mouse on it, well, it's not an interactive version, but if you keep your mouse on it, it's going to display which category is encoded thanks to this color. And here we have sorry, I lost my mouse. And here we have the amount of visible data, because we can filter on this tool, select the category. And here this allows us to keep a track on how many data are still available. There are also some interactive tool in this tool, interactive features, sorry. So we can decide to change the coloration of the view. Like, let's say we can click on different axes, so the view will be colored according to this variable. We can filter, as I was saying before, so we can use this icon to defilter, and we can select different variable to explore that in more detail. So now let's take an example of a kind of interaction we can do with it. So let's say we want to investigate more the Parkinson's disease cohort. So let's select the PD. Yeah, perfect. So now we have all the data recorded in the PD cohort, and we have 4 different algorithms here. We can decide to color according to the algorithm. So now each color represents an algorithm. We can see them all here. A tool I didn't present it before, we can decide to spread the table according to the coloration. So here, for example, instead of having the mean value of the overall data, we have the mean value per categories, group of ribbons, which allow us to have a bit more insight about what's going on. So here, for example, we saw that the yellow algorithm have a relative error around 9, whereas the purple one have a relative error around 7, which is more interesting. However, here on this axis, which is so the result of the algorithm, we can see that there is some value that are not on the axis. And what it meant is that basically this data could have not been computed. So there is like a bar that displays the amount of missing data in this specific variable. So it's helped us to balance our results. So if you only see as a relative error, for example, this algorithm seems more interesting, but there is also some missing data. So the question is, what do we want? So now let's focus on one algorithm. Here, I picked the yellow one. And let's say we want to investigate a bit more the results and how this works, so we can rely on the correlation plot here, balance band, but we can also wonder how a result more efficient depending on the different type of movement. So we can decide to color the view according to the type of movement here. So now yellow for small movement and bluer for longer one. And if we look on this representation here, it seems that the darker the color is, the lower the referential error, the relative error here. So and it's actually confirmed on this table here. So we have a relative error around 1 for longer walking path, whereas around 12 for shorter one. So it means the algorithm is more efficient on longer walking path. So maybe it means maybe small one will be like more messy. Well, I'm not an expert. So now as this is a kind of interaction we done on this tool, but we can go further. We can try to relate information, what is displayed here with like contextual factor, for example. So here we have a score, the on score that's related to Parkinson's disease diagnosis. I selected a subset of the data, so we have a better understanding of what's going on. So I didn't select all the different tests, but just like a small sample. And so we wonder if there is an effect of the score on the data. So far, we don't see much of a trend among the data, so we can decide to color according to the relative error to see what's going on the display. And if we go back to a ribbon that are colored according to the average value of the data that is used as a coloration, we can see that people with a score of 3 tend to have an overall value slightly higher than the others. So it's we go back to results that maybe know that maybe people with more advanced disease we will have more trouble to identify properly how they work. So it's among the results we can access thanks to this visualization. So, and we can also, for example, decide to click on an outlier and see what's going on, try to understand why there is such difference between the referential system value and the single sensor value. So we can access the detail I was saying before. And here, for example, we see that apparently the measurement had been on someone that was using walking aids. So maybe the use of walking aid can have like interfere with the result. So this is what the tool allows us to do. So this is all for my presentation today. I want to finish on the different perspective. So we're wishing to extend the use of this tool to other aspects of the project, like aggregation or patient involvement. Aggregation will be more like, for example, we want to access the data on a walking by level, on a daily level, maybe on a week level. So how could we use, how do the data will aggregate through the different hierarchical level? And we're also interested of how can we bring the data back to the patient, because the tool I presented now is dedicated to experts. So how to consider this when we're designing a tool for patients. And of course, we want to keep improving this tool, its interaction and its performance. So thank you very much for listening, and well, I'll go back to Claudia.
Thank you, Alma. It was quite a quick overview, but I hope that really the feeling that we wanted to give with this presentation is that how useful it might be when you have to deal with such type of data to be able to visualize them interactively, and possibly also do some analysis in a way that is immediately possible to access from this different perspective. So please, if anyone has questions for Alma, please feel free to type them in the chat. In the meantime, one thing that I was thinking might be useful, Alma, for people to know is how you developed this tool, because it's something that I know we had to develop in-house because we couldn't, there wasn't anything similar available that we could use for our purposes. So it would be interesting to share a little bit of what are the technical tools that you use for developing this software in this framework.
Yeah, this tool is actually developed in JavaScript, so we could share it among the different people from the consortium, and it's done thanks to a library named 3D.js. It's a library that allows people to customize visualizations.
Okay, and so it's something that runs in real time on the web, correct?
Yes, actually, yeah, exactly.
So the other thing that I think it might be worth commenting, because I know we have had a lot of these conversations throughout the development of the tool, is how you found it to coming from a perspective of a computer scientist that was not involved in the specific application that we are working on, so that of the mobility and the digital mobility outcomes. How did you find the interactions between, like, your background and the background of the people that you were working with in terms of input and how you implemented them?
Well, actually, first of all, I learned a lot from the background, and most of the time when you're confronted to a new background, a new domain, a new use case, I say, we tend to try to understand as much as possible from this background. But actually, what I learned with this project is not only I have to learn from people, but people have to learn from me in order so we can communicate. So I had to do a lot of presentation of what I was doing, because somehow I was expecting people to share all this knowledge without sharing anything back, and I discovered with just interacting with people help us to be able to build this tool and to provide such an analysis.
Okay. And so I don't see questions coming in the chat, so if there are no other curiosities from anyone, I think we can move to the next speaker, who is Francesca Salis. Francesca, please, the stage is yours.
Thank you, Claudia. If you attended the second webinar about the experimental tools, then you already know what is the Indeep system. However, I will do just a brief recap to be sure that all of you can follow my presentation. The Indeep system is a homemade multi-sensor low-cost wearable system developed by my research group at the University of Sassari. It includes magneto-inertial sensors which are positioned on feet and lower back. 2 pressure insoles with 16 sensing elements each, and 2 distance sensors with time-of-flight technology. As already explained in the third webinar about the experimental protocol, the Indeep system is used as a wearable gold standard for the 2.5 hours free living assessment. And for this reason, it was necessary to assess its performances in the estimation of the relevant digital mobility outcomes. With this aim, the Indeep was used in the laboratory acquisitions to be tested against the SP system and evaluate its accuracy. A preliminary evaluation involved 20 young healthy participants recruited both at the University of Sheffield and Sassari. And then the Indeep was tested using the technical validation study data, since our aim was to have a system suitable for the patients involved in this project. In the following slides, I'm going to show you part of the results obtained from the comparison with the SP system. In particular, I will show you the average results from the first 10 tasks, which are the, let's say, more standard ones. Then results from the SDA will be presented separately, since this test is more complex and challenging. The statistical analysis plan have been illustrated in detail in the fourth webinar. And in this presentation, we will look at a small subset of the metrics which are part of this plan. And it's important to know how they were computed to understand their meaning. And so here is a graphical representation before looking at the numbers. First way to compare the two systems is to compute the mean and standard deviation of the relevant digital mobility outcomes to have an idea of how similar the distributions are. And to do that, we know that each subject performs a battery of tasks. From those tasks, we obtain a series of walking bouts, and from each walking bout, we extract the relevant DMO. At this point, we can operate at different granularities depending on the level of detail that we want to reach. For example, at subject level. In our case, we are interested to an analysis at a group level, and so we consider the walking bouts from all the subjects of that cohort to compute the mean and standard deviation. A similar procedure can be followed to compute the median and the interquartile range values for the absolute error and relative error. So we consider the walking bouts obtained from one subject, from which we extract the DMOs and compute the absolute error and relative error. We do the same for all the subjects of the considered group, and then compute the median and IQR values for the absolute and relative error at the cohort level. In the second webinar, I already showed you the results obtained from young healthy participants from the first 10 tasks. In particular, we looked at the median relative error, and we saw that the numbers were very encouraging in accordance with previous studies. In fact, the error for duration and cadence was below 1%, less than 3% for the total length, and less than 2% for the walking speed. If we move to the SDA, as already said, this is a more challenging task, since the subject has to perform daily activities, and so the gait portions can be more irregular with a lower number of strides, which can be really small or even spurious movements. Looking at the data, this doesn't look so scary, so we can see that the errors are always below 5% for the significant DMOs. In particular, the walking bout duration is around 3%. The cadence is lower than 2%. The total length around 4%, and walking speed lower than 5%. Of course, the errors are higher with respect to those obtained from the 10 tasks, but this is reasonable considering the level of complexity. In fact, the correct walking bout detection is more difficult, and so also the error in the number of strides increases, and this leads, of course, to an increase in the errors for the other DMOs. Now we are going to see the results from the TVS analysis for the different cohorts of patients, focusing on walking speed, which is our primary outcome. This table shows the results from the 10 motor tasks regarding the walking speed for healthy adults in each cohort of patients. You can see that the median absolute error is maximum of 0.02 meters per second, and the relative error is always below 2.5%, which is, I can say, a great achievement. If we focus more in detail on the healthy adults and PFF patients, which are respectively the less challenging and more challenging groups, let's say, here you can see the correlation plot and Blend-Altman plot for the 10 motor tests for the healthy adults. And it's immediately clear that the two systems have an high correlation level, and the limits of agreement are more than acceptable for our analysis. Moreover, the distribution are almost stochastic, which means that the variance is independent from the type of test. The same can be observed for the PFF, since also in this case, the correlation is very high and the limits of agreement are perfectly in line with our requirements. Going to the Sda Set Test, you can see the same table, but for the simulated daily activities. And here the median absolute error is maximum 0.05 meters per second, while the median relative error is maximum around 6% for the majority of cases, except for the PFF. However, bear also in mind that in this case, you have lower speed values. And so for this reason, the percentage increase. If we look at the correlation plot and Blend-Altman plot for the healthy adults, we can see a correlation of 0.93, and the limits of agreement are higher in this case with respect to the 10 tests, but still acceptable, bearing in mind that the walking bouts included in the SDA have an average stride number, which is around 8 strides for the healthy adults. So we are analyzing very short walking bouts. And the same also for the PFF, we have still an high correlation, and the limits of agreement also in this case are really nice and acceptable, considering that for this cohort, the number of strides on average is around 11 for each walking bout. So if we do a summary, we can say that for the different motor tasks, the results were very good, both for the young healthy and for the groups involved in the TVS. We examined also the Sda test, which was challenging not only for the short walking bouts, but also because gait represents a small part of this test in which the subject has to perform different kinds of actions and activities. And we saw also in this case that results were very good. If we compute the same indexes considering all tests together, we obtain the following numbers. And we can see that even merging the tests, the results are really good. This, in conclusion, lead to the fact that the results of the Indeep validation have shown a good level of reliability for different types of motor tests with various complexity levels, mainly including gait. For this analysis, we considered walking bouts of different length. In fact, were included also walking bouts with less than 10 strides. So in this sense, the results I showed you are guarantees of the good performances of our system. The errors are independent from velocity. In fact, we analyze tasks and groups with different gait speeds. I can give you the range of average speed for the groups, which goes from 0.63 meters per second to 1.17 meters per second. Moreover, the algorithm resulted to be accurate and robust, both on healthy participants, so young and adults, and on patients with different diseases. In fact, we obtained for the walking speed median relative errors, which go from 2.02% to 2.58%, considering all the groups. So I think we can be proud of our job, of what we did. So thank you for your attention, and now I'm happy to address your questions.
Thank you, Francesca. One thing that I think might be interesting to comment on, Francesca, is how when you started processing the data from the real world, whether there have been situations where the system was challenged differently than what we observed in the lab, because as you know, as you correctly showed, like the simulated daily activities, what you call the SDA, were really already designed to be really challenging. We did that on purpose because we wanted to have the trickiest possible conditions to test the system in. But when you went and started processing the data from the real world, what were the real challenge for the system?
What I can say is that, of course, in the laboratory, you know more or less what happens, because even if the protocol is challenging, there's a specific guideline to follow, while out of lab, you have only some tasks which are given as guidelines, but the subject can do anything he wants. And so let's say I had to expect activities which could be wrongly identified as gate. And so, for example, a PFF participant during the 2.5 hours acquisitions participated to a rehabilitation session, and he used the elliptical machine. Of course, this is not gate, but this is a periodic movement like gate, which can trick the algorithm. And in this context, the toolbox developed by Alma was really useful, because it allowed us to detect all the outliers and understand in each case which was the nature of the outlier. And so, for example, in the case of the subject who used the elliptica, it was possible to add further checks to the algorithm and make it more selective, to avoid the inclusion and the recognition of gate-like activities. So I think that this was the most challenging part.
I can see how an elliptic machine can be similar to gate. The other questions from the audience? Okay. No more questions, so I think we can move to the next presentation. If more questions come to mind in the meantime, please write them in the chat. We have more time also later for discussion. As I mentioned in the introductions, we started with many algorithms that we have introduced, and then Karma has been working on ranking these algorithms and choosing the best one that we will then bring forward to our clinical validation study. And so Encarna is going to tell us about this, how she tackled this problem and the results that we obtained. Please, Encarna.
Thank you, Claudia. So yes, so the topic of my talk is the top ranked algorithms within Mobilise-D. And I am Encarna Mico from Newcastle University. So to understand how we rank the algorithms available in Mobilise-D, first, we need to understand how we validated the DMO, or digital mobility outcomes, obtained from the IMU or single sensor unit as well. For that, we were using as a reference system the stereophotogrammetric system in the lab and the Indeep that Francesca just presented in the free living conditions. As already mentioned in previous webinars, the full pipeline implemented in Mobilise-D has as an input the IMU data. And this is processed in several blocks of algorithms, each in charge of estimating particular DMOs or information required for the next block of the sequence. In the case of the ranking, we had to consider 7 particular blocks for which we had several algorithms provided within the within the consortium. For the gate sequence detection, we had 8 algorithms. For turning, we had a single algorithm. For step detection, we had 8 algorithms, although initially we had 20 of them. For left or right stride detection, we had 4 algorithms. For step or stride length, we had 19 algorithms. For cadence, we had 21 algorithms. And for real-world walking speed, we had the combination of the top 3 from the step length and the top 3 from the cadence. So the combination of all the blocks that already were presented in the webinars, considering all these blocks, will give the walking bout assembly, the final block. So let's see how this was assessed. So for a particular or individual block, let's say step detection, for which we had 8 algorithms, we had an input, either the IMU data or the data from the previous block. In the case of step detection, we had the data from the previous block. And then we had an output. This output was considered for validation by comparison to similar or corresponding outcome from the reference system. And based on this, we set the operational methodology to rank the algorithms. So the ranking methodology accounted for different factors. At each methodology, or this methodology was adapted to each of the blocks, considering the heterogeneity of the statistical variables and DMOs for each specific block. But let's assess this ranking methodology in general terms. What we considered was the number of participants, the gate speed, the accuracy of the reference system, and of course, the performance metrics and criterion validity derived from the validation of the outcomes. And all this information was combined to provide a single normalized overall performance index for a specific cohort. Therefore, we had a specific performance index for a specific cohort and for a specific block. 0 will be for the worst and 1 for the best. In that way, we could rank the algorithms from 0 to 1, from the worst to the best. The first step in this methodology was classifying all the subjects from a specific cohort based on gate speed. So we classify them as fast walkers when their gate speed was more than 1.5 meters per second, middle walkers with a gate speed in between 1.5 and 0.5 meters per second, and slow walkers, those with gate speed below 0.5 meters seconds. So the 3 steps marked in orange in this slide correspond to the process that we will apply for a single group based on the gate speed of a specific cohort. The first step is assessing the criterion validity. I'll give more details in the next slides. The second, we scale it by the performance score. The third, we scale it by the dataset score. And all this will be combined on a single value for a specific group based on the gate speed. And considering all the subgroups, the fast, middle, and slow walkers, within a specific cohort, we will scale them, each of them for their own group score to obtain a single normalized overall performance index for a specific cohort. I'll give more indications and more details in the next slides. So the first step, the criterion validity, using as an example the step detection block for which we had 8 algorithms. So in this block, we had to consider 5 statistical measures, which were relative error of step duration as an average, relative error of step duration as a standard deviation, interclass correlation coefficient of step duration, sensitivity of initial contact events identification, positive predicted value of initial contact events identification. So in this case, or this particular block, we had these 5 statistical measures. Each of them had assigned a weight. Why? Because each of them will be ranked or will be considered as a more or less important relatively to the other statistical measures. But we also need to consider whether they are cost or benefit, which means the higher the worst, which will be in the case of relative error or step duration, cost, or the benefit, the highest, the best, as is the case for interclass correlation or sensitivity and positive predicted value. So all of them had to have the same direction, either benefit or either cost. So we decided to go for benefit. Remember, 0 the worst, 1 the best. So the highest, the best will be considered for our ranking. So the cost, 2 variables will be transformed in a way to be considered as a benefit. So the highest, the best. All this information was scaled by the performance. The performance took in account how the algorithm was addressing the subjects and also the walking bouts. So was each of the algorithms able to be run and provide DMOs on each of the subjects as well as each of the walking bouts? Remember, as Alma showed in her previous presentation, that in some of the cases, the algorithms, like the purple one that she showed, were very good in performance, but they were not run in all of the walking bouts. So in this case, this performance score will address this issue. And finally, the dataset relative contribution. This step was not considered for the technical validation study of Mobilise-D. However, I decided to mention it here because it's very important for a ranking methodology when considering heterogeneous datasets. So in the case of having different datasets, as we had in Mobilise-D previously to the technical validation study, we had to consider what was the percentage of contribution of each of the datasets to the final analysis. And for that, we had to group the participants based on their speed. We had to check the percentage of each subgroup in the dataset. And we had to assign a specific score to the type of reference system, either as a gold standard, 1.0, or either considered as a silver standard with a weight of 0.5. And we obtained a dataset score for each subgroup for the fast, middle, and slow walkers based on this information. Moreover, in case of counting on free living datasets, the environments will be rated higher, 1.0, whereas the lab will be rated with a 0.5 score. So the final step was scoring by the data score. So these 3 steps were applied for each of the groups of the cohorts, for the fast, for the middle, and for the slow. And each of them were assigned a group score, which was scaled by all the information obtained within the 3 steps. As you can see, the slow walkers had the highest score because they were the most challenging, and therefore we assigned a 0.5. The medium walkers had a score of 0.3, and the fast walkers, supposedly to be the easiest, they had a weight of 0.2. So each of the 3 information combined will be scaled by each of the group scores. And finally, they all will be summed in order to have the single normalized overall performance index for a specific cohort in this specific block. So what is the podium of the algorithms? So for the gate sequence detection, the first algorithm was presented by Ilutz and colleagues and is using a frequency-based approach. The vertical and anterior-posterior acceleration signals were band pass filtered to 0.5 to 3 Hertz, and are the relevant gate frequencies. You can see like the blue plot that we're obtaining from this. Afterwards, we perform a convolution with a 2 Hertz sine wave representing a template for the gate cycle, as you can see in the green plot. And the peaks in the convolution result, the red, represent the gate cycles. And if a reasonable number between 2 and 15 appear in that specific window, it was counted as a gate sequence. The second algorithm, sorry, I forgot to mention that this first algorithm was ranked the best for the healthy adults and COPD groups. They're relatively considered as the faster walkers among all the cohorts within Mobilise-D. Whereas for the gate sequence detection 2, that we obtained for the 3 cohorts considered the slower walkers, Parkinson, MS, and postural prefemoral fracture participants. So in this case, we had the algorithm from Parsichev Ionescu from EFPIA, one of the partners of Mobilise-D. So this approach was developed by Anisoara, and they used the accelerometer norm to be orientation independent. and first apply some advanced filtering techniques to enhance peaks that are related to steps, as you can see the red crosses in the plot. Those peaks are then detected and represented subsequent steps that are summarized to gate sequences, represented or marked in yellow color. For the step detection algorithm, we use the very well-known and famous algorithm from McCamley, which uses the vertical acceleration. And this acceleration is smoothed by integrating and then differentiating the acceleration signal using a Gaussian continuous wavelet transform. Finally, the detection of signal minima represents the initial contacts. This algorithm was improved by some of the frequency techniques developed by Anisoara, filtering specifically the signal to enhance the peaks. The stride length was again based on a very famous article published by Salstra and Hoff, which applies the inverted pendulum principle in order to get the step length. Based on that, they derive the stride length. However, our colleagues from EPFL optimized empirical corrections with a machine learning approach. For Cadence, we had a similar situation as for the gate sequence. We had a first algorithm ranked for the fast cohorts within Mobilise-D, healthy adults and COPD. In this case, we had the algorithm proposed by Shin and Park, which used a zero crossing technique, again based on the accelerometer norm. In order to reduce noise, the sliding window summing technique was utilized, basically applying a low-pass filtering. The acceleration differential technique was also utilized to eliminate the effect of gravity, high-pass filtering. And finally, the zero crossing on the positive slope was detected and determined the initial contact events, as you can see in this figure. Cadence 2, the second algorithm, which was selected for the three slower cohorts within Mobilise-D, PD, MS, and PFF. In this case, once again, we had an algorithm proposed or developed by the EPFL partner, Parasichev, Ionescu, Ani. And this second algorithm was proposed for the estimation of cadence based on, first, a Savchitsky-Golay filter, followed by the retrend of the three signals. Second, by performing a continuous wavelet transformation, which was low-pass filter. And finally, by applying a Gaussian smoothing and a morphological filter and a difference of the signal. All of this to provide the cadence likelihood estimate. For the left-right detection, which means to identify whether an initial contact is from the left or from the right step, Ulrich et al., again from our Mobilise-D consortium, developed an algorithm based on machine learning-based approach. And this was implemented on gyroscope signal data from the vertical and anterior posterior direction, capturing the rotation of the hip during walking. Some processing to smooth the signal and then was implemented. And then we look at some signal characteristics at the points of the initial contact events, as you can see in the gray lines. Finally, we calculated these values for the pre-computed initial contact events, and then they were fed into a machine learning classifier, which made the prediction of which of these initial contact events belong to the left or to the right foot. And finally, the last algorithm that we ranked was the turning detection. But in this case, we had a single algorithm. Therefore, the ranking was quite clear. Only El Gohari was the one. This algorithm was based on the gyroscope axis that captures the rotation around the vertical axis. After some signal smoothing, maximizing the signal were detected, and these were potentially represented turns. Corresponding 5 degrees crossings before and afterwards determined start and end points of turnings, and after some final checks were performed in order to check the turning sequences like shown in red in the plot. They also calculated the turning angle and observed whether this was within 100 to 180 degrees turn. So as you can see, the pipeline was more complex than it looked at the beginning. So we had 2 pipelines based on the characterization or on the ranking that we obtained for each of the blocks. So considering the faster walkers cohorts within Mobilise-D, COPD and healthy adults, we had the pipeline 1, you can see on the top of this slide, whereas pipeline 2 was considered for the 3 slower cohorts within Mobilise-D, MS, PD, and PFF. So the first block was the pre-processing, and this was a single block implemented for all cohorts. However, for gate sequence detection, as already mentioned, we had 2 different algorithms, ELUDE for the faster and Parasichev-Ionescu for the slower. Turning detection was the next step, and this block was a single one provided. For step detection, we obtained only McCambly as the best ranked for all the cohorts. Therefore, we had only one. For Cadence, as similar as for gate sequence, we had 2 options, Shinhan Park and Parasichev-Ionescu. And finally, for left-right detection and stride length estimation, as well as high estimation, we had a single algorithm. The combination of all these blocks and the selection of the best ranked algorithms permitted to obtain what we call the walking bout assembly, which was the definition of a walking bout based on the consideration of all spatiotemporal characteristics determined on the previous steps. And all this permitted to obtain at a walking bout level digital mobility outcomes as well as secondary outcomes. The next speaker, Tekla Bonci, will show how these 2 pipelines have been shown to be sensor agnostic. Thank you.
So thank you, Encarna. And now I'm going to talk about how we can prove whether our pipeline is device agnostic, which is a concept that has been mentioned since the very first webinar of this series. So, as Encarna has just shown, we got our definition-driven pipeline that is made by different steps and blocks, and based on the ranking procedure on the different cohorts included in the technical validation study, we've been able to identify different cohort-specific pipelines, which resulted in being 2 main pipelines that hereafter are going to be called P1 and P2. And if we want to actually prove whether our pipeline is device agnostic, what we can do is simply feed the pipeline with the signal that is captured by a different device. But when we are going to do this kind of exercise, there are different aspects that we should consider. First of all, before actually going to look at which are these steps, we need to make sure that the data that is going to be fed in the pipeline is going to be at least signal from a 3-axial accelerometer and a 3-axial gyroscope data. And then the way in which the DMOs are going to be estimated might differ due to the fact that we might have differences in the device electronics, as well as differences in the attachment modality, as well as difference in both of them, so both the electronics and attachment modality. But if we want to assess specifically how and whether the pipeline is device agnostic, the first point is the crucial one, because this really is going to tell us what is happening, just changing a specific feature in the input data. And for actually assessing whether we have differences in the electronics of the devices, we can use the procedure that was clearly presented in the second webinar by Marco Caruso, where we can use both static and dynamic acquisition to actually assess the metrological feature of the devices that are used in the data collection. And in terms of the data for doing this kind of exercise, we can use our technical validation study, because if you look at the protocol in both the assessment that we had in the lab and in the free living condition, we had 2 sensors that were rigidly attached with this specifically designed case on the lower back with an elastic belt. So this dataset really provides us with the ideal dataset to assess whether our pipeline is device agnostic. And this can be done especially because the two devices that are rigidly attached are quite different from a methodological point of view. And again, this is the slide from the second webinar, where we can see that the Indeep and the McRoberts device are quite different in terms of methodological feature, especially for the gyroscope data. And in terms of data processing, we applied the two different pipelines that Encarna has just presented. So the pipeline P1 has been applied on data that have been captured both in lab and in the free living data for the COPD and the healthy adults. And the pipeline 2 has been applied to data captured in the two same conditions for Parkinson disease and proximal femur fracture data. And this has been done using data collected with the McRoberts sensor, as well as with an inertial unit of the Indeep system, which is methodologically superior, as we've seen before. So let's have a look how this data processing actually look like. So we got the signal from the first device that is fed into our pipeline, and then we extract the digital mobility outcome at a walking bout level, which means that when we can recognize at least two left and two right strides, we can identify a walking bout, which includes level walking, turning, and incline walking as well. And the same procedure is done also with the other device. And then we are going to compare the real walking speed values, which is our primary DMO, for those walking bouts that were detected by both systems. Before going into the results, I would just like to show you an example of the raw data that we can measure with those two devices. Here we have an example of the three components of the acceleration recorded with the McRoberts sensor. And if we superimpose the signal of the Indeep, we can see that they are almost the same. And if we are going to zoom in, we can clearly see very small differences for the acceleration signal. So when we run the two pipelines, so P1 and P2 using the two devices for the two conditions, we can see that in terms of walking bouts identification, we had a similar number of bouts that were recognized. And although, for example, in this case, we do have a slightly different number of bouts, if we are looking at the overall real walking speed that was obtained in terms of mean and standard deviation, we can see that the estimations are exactly the same. And now if we are going to compare the results at a walking bout level for the real walking speed estimated with the two inertial sensor units with a correlation plot, we can see that we have a perfect agreement between the two systems. And if we are going to further explore the differences using a Bland-Hartmann plot, we can see that the limits of agreement is really good because we are talking about 0.08 meter per second difference in terms of upper limit of the limits of agreement. But what we can do for this pipeline that was run on the COPD and the healthy adults data, it was to explore those points that belongs to the upper and lower limits of agreement. And we can see that most of those belongs to the free living data, which is not surprising because most of the bouts actually belonging to this kind of condition. But the most important point is that most of these bouts are actually belonging to the short walking bouts, those that are shorter than 10 seconds. And this is a very important concept that is going to be stressed in the next presentation, because our algorithm are going to be more reliable, especially for the spatial information on the longer bouts. So if we are going to repeat the same analysis, removing those shorter bouts, we can see that our results are even greater than what we had before, both in terms of limits of agreement and in terms of relation coefficient and coefficient of determination. And we can notice that really almost all the differences are below 0.1 meter per second, which is really great. And although we are losing some walking bouts in this kind of analysis, we still have a nice representation of both bouts that belongs to the free living and the laboratory assessment, as well as a good distribution between the two cohorts included in the analysis. When the second pipeline was run on data belonging from Parkinson's disease and PFF data, we can see that similar results were obtained. And again, looking at those points that are above and below our limits of agreements in the Blandman plot, again, very low differences. We are talking about less than 0.1 meter per second. We can see that those bouts, again, belong mostly to the free living condition, and even more of them actually shorter than 10 seconds. We are almost looking at 90% of those points in those two regions here. So again, if we are going to remove those bouts shorter than 10 seconds, we can see that we really have an amazing agreement between the two systems. And again, we are still keeping a good balance between the bouts observed in the free living and in the lab, as well as between the two cohorts included in the second pipeline. So our good and strong, let's say, take-home message is that our pipelines can be considered device agnostic. And this is true because the algorithms that are included in the pipeline can provide estimation of the real walking speed that are equivalent, even though when the algorithms are run with data that are collected from devices, including sensors that are quite different from a metrological point of view. And another important point is that the results were even more satisfactory when we are going to consider bouts that are longer than 10 seconds. Thank you for your attention. Now we are happy to take any question that you might have, both related to this question and the one related to the previous presentation.
Thank you, Tekla. I would really encourage our audience to type in the questions. In the meantime, I was thinking maybe Carla might be worth it adding a few considerations around. You have been processing data from so many algorithms, and we have this objective, robust methodology that you have presented. But I was wondering how close the results were, and like, you know, if you can tell a bit more about the process of how you ended up working with those results that might have been really close in deciding which would be the best algorithm.
Yeah, so this is a very good question. Normally, we first selected the top 3 ranked algorithms, and we discarded any other which was not qualified as at least within the 3rd position. And among the first 3, we looked at the data based on the toolbox from ALMA. And we were looking at the different statistical measures that, as I mentioned, were considered on the weights. So we had kind of the most important statistical measures, which had a bigger or lower weight, also based on the consortium. So I didn't mention this in my presentation, but before we provided all this analysis, the consortium was part of a questionnaire that actually Tekla developed, and together with other people. And they were asking questions about what were the statistical measures they consider more important. And based on this highly weighted statistical characteristics decided by the consortium, they were the ones that we, of course, used for the ranking, and the ones that we observed through the visualization toolbox of ALMA in order to decide, well, is our top 1, top 2, or our top 3 ranked algorithm actually the best? So we were actually diving a little bit more into the resource with the visualization toolbox.
Thank you. And yeah, so the other thing that I think is worth, again, Tekla stressed that, well, already quite significantly for her comparison, but I think it might be interesting also to come to discuss a little bit how we got to that point of our 10 seconds threshold, and how this, which were the blocks we observed this being like a critical factor for.
Yeah, so there were some blocks for which we observed that short walking bouts, so those below 10 seconds, were more challenged. And these were like especially the stride length, and I think also real walking speed was slightly more challenged for those walking bout durations of shorter duration. However, we saw that, for example, Cadence was quite robust over all the different ranges of duration. And I think we also ended up observing this by the toolbox of Alma, because she provided the different colors. We could color the different results based on the different ranges. And also we could see the different statistical measures for each of the ranges, also based on her toolbox. So we could very fast observe how the results change depending on this walking bout duration. And indeed, step length and real walking speed, they were the most sensitive to these shorter walking bouts, whereas cadence and step detection were a little bit more robust.
Yeah, and just to add on that, maybe the other thing that we have been discussing a lot through the project and looking at those data and those results in details, there were really two elements, I would say, that affected our results. So one was this duration, and the other one was, of course, the presence of turns or like less rectilinear path, which we were able to identify thanks to having the gyroscope. And I think that this is another important point to stress at this stage, that we found that really useful. So having the possibility to have data not just from the accelerometers, but also from the gyroscope in the real world was really making a difference in terms of the ability to understand which factors should be considered more or less reliable. And this is something that we will still be doing in the processing of our 7 days data. Yeah, right. No.
And again, also we were looking through the visualization, different ranges of turns present in the walking bouts, and especially left and right algorithm, because it's based on the gyroscope data, as well as step length. They were quite sensitive to the number of turns present on the walking bout durations. And it was also very interesting to see how the presence of turns could affect the specific characteristic or statistical validation outcome when evaluating the presence of these turns. So indeed, it's something very important that we observe.
Thanks, Encarna. So I see that there is a question from Jaya asking how the real-world estimate considerations play into the DMO's performance. So, for example, patients with active lifestyles, say still employed versus sedentary lifestyles, say at home, institutionalized, and the algorithms rating to measure disease progression and the like. So this question is really something that we are going to look into more details now when looking at the data from the clinical validation study, in the sense that at this stage of the project, we were really more interested in understanding just the accuracy on the individual single bouts that we are processing. So we are not really looking into detailed classifications detailed about what the patients were doing specifically and in terms of lifestyle and the full week analysis. This is something that we will start doing now that we know which DMOs we can calculate in a reliable manner. So I will have to say that unfortunately we need to wait a bit longer to be able to answer to your question, Jaya, if I understood that correctly.
Yeah, but still we saw that some of the results, at least for Parkinson's disease and some of the clinical profiles, we could see that those with worst clinical profile were having a worse validation of the outcomes. So although Claudia is totally right, we will look at a little bit further in detail. We already observed some patterns on, at least in clinical scores.
Yeah, of course. So the most impaired patients, of course, were those for which our algorithms were most challenged. So those that had the most irregular walking patterns. Linda, is there a question? Just saying that she's pleased to hear that the data reflect the function of these types of patients. Actually, Linda, I would like to say this is really something that we know that somehow can be seen as a difficulty, what we are suggesting, which is using different data processing pipeline for different type of walking. But we were really expecting this to happen. We know that we cannot use the one size doesn't fit all, and that our patients have different walking conditions. That is not just the speed that counts, but it's really the complexity of the walk. And the reason why we decided to work with cohorts that are so different from each other is really to make sure that we have something that reflects the possible type of function. So thanks for pointing that out, because it's really one of the things that we were set to achieve. Peter, people seem to have preferred walking speeds when measuring in free living over several days, presumably related to indoor and outdoor walking. How is this taken into consideration? Taking a mean gauge speed might not suit this. Again, Peter, I fully agree with you. This is something that we are now starting to look at. So there is a group that has started working now that we have the algorithms that work in looking at our 7 days data and looking at how what we call the aggregation level that is ideal to process this data. So we will be looking at how things change, whether you use 1 bout, 1 minute, 1 hour, or the data from the entire week, and whether the mean is the right value or not. So, and concerning the indoor and outdoor, in those 7 days, our patients were also wearing a mobile phone that was used exactly to do this sort of classification. So we are also interested in looking at whether we obtain the same type of consideration in that sense. And of course, what we are observing for most of our algorithms, this famous 10 seconds threshold that we have been talking about, is something that is much more likely to happen if you have a bigger house or if you are outdoor. But there are certain DMOs that can work for less than that, even if the bout is shorter. But if you look at walking speed, anything below 10 seconds doesn't really make sense. That's what we are seeing in our data. Lorenza, I think, Tekla, you can take this question probably. Did test the algorithms when the running belt was not tight enough, for example, and yes, how was the performance? So, Tekla, you might want to talk about the future plans for this.
Yes, because when we are going to have, let's say, a further analysis of our pipeline in saying whether the pipeline is going to be device agnostic, we would like also to see which is the effect when the sensor is attached in a different way. So we are going to have a specific data set in which we have the same sensor that is going to be attached to the skin, and another sensor that instead is going to be attached with the elastic belt. We don't have specific data when we can say specifically whether the belt was, perfectly tight or not. This is something that we should further explore with a specific data set, but at this stage we cannot go too much in detail with the data that we got so far.
And yeah, just to add on top of that, for us, the concept until now is what we said, but it was always like, we are device agnostic, provided that the device is worn in a certain manner. In our case, the belt we are using is not extremely tight, and the results, the data that we collected during the 2.5 hours, we also asked our participants to if they had to go to the loo, for example, to just do it. And that's a typical thing, the typical example where the belt was probably moving around and this sort of thing. So we do have data that are quite dirty in that sense, that reflect what would happen in the real world. So everything that we have collected in the 2.5 hours reflect as much as possible the variation that we would expect to see in the 7 days. Of course, it's not going to be the same, but that's the attachment of the sensor is definitely an important factor, and it's something else that we will be evaluating in the coming weeks. Are there other questions? Good. If not, I think we can move to the next talk, which is, again, Silvia is going to give us even more insights into the results that we are obtaining that possibly might even answer some of the questions that we were discussing. So Silvia, please.
Thank you very much, and thanks for all the speakers, because I've got an easy job now with these great introductions. So today, really, I'm going to talk about the results that we obtain measuring walking speed in the real world and also in the lab in different health conditions. And then the message would be that obviously one size does not fit all. So just a refresher about the technical validation study protocol and the data. We know that we have been measuring data on 5 clinical cohorts and healthy adults. We have neurological cohorts like multiple sclerosis, Parkinson's disease. We've got like a slow walker, like congestive heart failure and chronic obstructive pulmonary disease. And then we've got also a proximal femoral fracture, so people with quite a lot of gait impairment. And just a reminder of the previous webinars about the technical validation study protocol and the variety and the comprehensive assessment that were done, both clinically and also mobility assessment in the lab and in free living condition, both during 7 days and the 2.5 hours free living assessment. Today, what I'm going to show you is, if you want, the results that we obtain between the two, if you want, different way of looking at mobility. One side, if you want, of the spectrum with healthy adults. So if you want like sort of easier data to deal with, and the other side of the spectrum with very, very impaired proximal femoral fracture participants. The focus that I'm gonna have today is looking at in-lab assessment and also the 2.5 free living assessment, where we did have reference system data as well to compare our single sensor to. So in terms, just a little bit of a reminder of the in-lab data. In lab, we had quite a comprehensive protocol that comprises, obviously, the simple, if you want, straight walk, to more complex walks, including a lot of turns, and to the most complex structured activity assessment and task that Francesca showed you before. In the lab, we're going to obviously compare our single sensor versus the stereophotogrammetric system that is our reference system. For the real world, for the 2.5-hour assessment, we are going to look at participant dealing with the everyday life in 2.5 hours, so going about their sort of activity, and the reference system that we're going to use is the Indeep system that Francesca described before. In terms of this data set, this is just an overview of what we sort of obtain, and these are, again, preliminary results. So we have the proximal femoral fracture group and the healthy or the other groups. I have highlighted here that we have a specific total of walking bound number. This because the sample size evaluation was not based on a minimum number of participants, but actually on achieving a minimum number of identified walking bouts, including the in-lab and out-of-lab data per cohort. This was to be able to achieve robust statistical analysis. And specifically, we targeted an ICC of greater than 0.7, and the minimum walking bout that we identified was 401. So we exceeded that number, so we know that we are statistically powered to do this analysis. As you can see here, I have highlighted just a few demographic data. So obviously, the proximal femoral fracture cohort was older, and there's an inclusion criteria that have to be within 12 months from surgical treatment, which is important. Also to know that a lot of our PFF participants were actually inpatients, so still at the hospital at the time of the assessment. And in terms of walking aid use, we know that healthy older adults didn't have any walking aid uses, but then the PFF cohort had almost a third using either crutches, walker, or rollator. So quite complex, if you want, impairment and biomechanics there. In terms of the actual severity of the PFF cohort, we use the short physical performance battery, which measure gait, balance, and sit-to-stand activities to really characterize, if you want, mobility and lower limb function as well. And as you can see, SPPB was quite low in this cohort. about the outcome. So we are going to present results about walking speed and how was it evaluated. Encarna and previously in the previous webinar, you have seen that it's quite a long process. We are obtaining walking bout, and then in that we can look at walking speed. The digital mobility outcome that we're going to look at is walking speed, which is obtained as an average of the stride speed for each walking bout. So stride speed, just to know that stride speed is derived from stride length and cadence, and I'm going to touch upon this later on to show how, if you want, stride length really performances did impact on the performances also of walking speed. Just a reminder of the statistical analysis, because I think it's important. We mentioned this in the last webinar, but what we're going to show you today in terms of criterion validity and performance metric is obviously looking at relative error, looking at agreement with the intra-class correlation ICC, and then statistical significance between, if you want, reference system and the single sensor data. We're going to also have the chance using Dr. Armakantu visualization tool to really look into more in-depth agreement, looking at the Bland-Hartmann plots, scatter plots, and histograms as well. Just a reminder of the level of analysis that Francesca touched on before. In the previous time, I sort of mentioned that we will do, and we have been doing an analysis based on all identified walking bout, both from the reference system and the single sensor, regardless of whether they are true positive, false negative, or false positive. So whether they are actually indeed correctly identified or not by the single sensor. And in this way, we can really look at results at the patient level and then at a cohort level. And then, as Francesca mentioned before, we really can base the analysis on the true positive walking bout. So only on the walking bout that are positively identified by the single sensor, so that we can have a like for like, if you want, comparison of the walking bout and really have results at the walking bout level that, as I mentioned before, is our unit of measure and really our interest. And today I'm going to show you the results based on a walking bout level, also because a few of our statistical analysis like ICC and statistical significance do require this. So first of all, a look at the results in the lab. So I'm here, if you want, pulling all together the data coming from all the different tasks that I've mentioned before. And we're going to look at, as I said, the single sensor versus the stereophotometric system as our reference system. As you would expect, the relative error for the healthier of the adults is lower, around 14%. There's no statistical difference between the walking speed as evaluated by the reference system or single sensor. And for the PFF, again, reminder that we have almost a third of participants with using walking aid. We can see that the walking speed was slightly higher, so there is an overestimation from the single sensor, but that's not significant. And the relative error is, as expected, higher. This is obviously because of the difficult biomechanics of the gait and the gait impairment. If we look a little bit more in depth at the effect of the type of test or task in the lab, we can see that here we have different color for the different laboratory task. And we can see that for the, say, if you want simple, more simple task, we have a lower, obviously, limit of agreement and a better agreement between the two, if you want, single sensor reference system. And if we look in depth, the activities that possibly were most challenging, also for our algorithm and our pipeline, were obviously the simulated activity, as seen here, both for the healthy adults and PFF, but also for the PFF cohort, L-test and fast walk. This obviously would really impact on the biomechanic of their walking, especially if they're using walking aid. And because, to some extent, a picture is worth 1,000 words, what I wanted to show you, not being able to show you the actual video of our participant, I can show you an example of raw signal during an L-test, where participant had to, from a sitting down position, had to stand up and go around doing 2 different turns. And as you can see, whether we can actually have a quite a good, clean signal from a healthy participant. As you can see here at the lower, the bottom of the screen, this is an exemplary signal from a participant from the PFF cohort using a rollator. And as you can see, obviously the range of the signal of the acceleration is lower. Obviously it takes longer for this participant to do the test, and obviously there's a variety of really shuffling and quite noisy signal as well. So our algorithm did do the best, I would say, in this condition. In terms of the results in the real world, we can really, first of all, characterize the walking bout that we're dealing with. And as mentioned before, we look at all walking bouts pulled together and then a different bout length as shown in the previous webinar. So bout length less than 10 seconds, 10 to 30, 30 to 60, 60 to 2 minutes, and then over 2 minutes as well. As expected, the number of walking bouts for both cohorts did decrease as the walking bout length increased. Number of turns also increased with the increase increase of the walking bowel length. And as expected and mentioned before also from Tekla, the highest relative error in terms of walking bowel duration was found for the bowels that were very short, less than 10 seconds, because of obviously of the noisy and obviously of the difficulty in this. So what we consider and what I'm going to show you from now on is all the results that we obtained in the real world, so in the 2.5 hours assessment for all the bowels greater than 10 seconds. So here are the results, walking speed. So let's start with walking speed, and then I'm going to go through cadence and stride length, which are, as I said, the two component domains that make up, if you want, walking speed. So in terms of walking speed in the real world, we can see a fantastic, I would say, results in terms of relative error, so around 11% for healthy adults, and obviously a higher relative error, around 20% for the PFF cohort. And for both cohorts, walking speed was overestimated by the single sensor. ICC, there's an excellent agreement for healthy adults, and obviously lower agreement, moderate for the PFF. But let's see, if you want, the temporal side of walking speed. As mentioned before, cadence was actually very, very robustly evaluated. As you can see, there is a slightly underestimation for both the cohorts, but a fantastic relative error, which is around 4% for both cohorts. And I would say a very good to excellent agreement between the two. So really, if you want, the to some extent higher error for both cohorts was really driven by the stride length. As Encarna mentioned before, stride length was evaluated using an inverted pendulum model and obviously sensor vertical acceleration integration. So again, stride length was overestimated for both cohorts, and the relative error, as you can see, was higher, 12% for healthy adults and 90% for the PFF. But although we were not, to some extent, really focused on looking at disease severity, what is interesting to see is that for the PFF cohort in real world scenario, obviously disease severity play a role. And we can see here as for the lowest score of the SPVB, so for the, if you want, highest impact and highest severity of the PFF cohort, we had higher bias as well and higher error. And if you look at the contextual factor as well, if we look at the walking aid use, we can see that how this has a massive impact on our results. Here are all the results, and you can see the correlation of 0.67 between the single sensor and the reference system. If we look at the Blandman plot, we can see that people using walking aid are the ones that are, if you want, dragging the sort of limit of agreements higher, and they have the highest of the errors. So if we do remove, if you want, this participant, and if you just focus on people that are not using walking aid, although in this sort of impaired cohort PFF, we can see how correlation increased dramatically from 0.67 to 0.88, and the limits of agreement reduced as well. So just a summary as a take-home message: how accurately can we estimate walking speed? And it depends, and hopefully I've been able to show that it depends on the population of interest and the level of gait impairments, the difference in performance from the healthy adults and PFF cohorts. On the environment, the laboratory and versus the real world are different. Obviously, if you want, this is also impacted by the type of the lab-based task, with, if you want, more difficult and complex tasks being sort of the one that are dragging the performance down. Obviously depends on walking bowel length, with longer walking bowels, especially the one greater than 10 seconds having, you know, lower error respect to the lower one. And then on disease severity as well, and on contextual factor. And in this specific case, in the PFF, walking aid use did really impact the results. So obviously we're going to do a little bit of more work in the future, specifically giving also recommendation also for other DMOs, also, for example, gait phase, swing time, stance time, and other DMOs that I presented in the last webinar. So thanks very much, and any questions?
Thank you, Silvia. While we wait for questions to come through the chat, I think it might be worth it to just comment on briefly. I know we decided not to present everything today due to time and also because we're still working on the data, but just a little bit of comment on how things are going for the PD and DMS patients.
Yeah, so actually we can say that the results that I presented today for the PFF are actually the higher error, in the sense that for the other neurological core, for example, for PD and MS, we had a relative error around 11 for the PT and a little bit higher, around 17% for the MS cohort. We know that previous work have shown that, for example, you can have much lower, if you want, error if you are in the lab and if you're using, for example, sensor or, on shank, on feet. And so we know that, for example, Trianello showed that there is around a 3% of error there. But obviously our protocols were much more challenging and much more, if you want, stressful in terms of our algorithm performances. And then if we look at one of the recent publication by Mobilise and Abu Fazl Sultani that use actually the same algorithms also presented today, we could actually see that although the results were really based on in-lab scenarios, but actually the performances were quite similar. So around the 20% also in lab sort of relative error, specifically for very impaired cohorts. In that case was people with obviously post-stroke, not PFF, but still, if you want, to some extent similarity around, you know, asymmetry and gait impairment.
Thank you.
No problem.
So I don't see questions coming through the chat, and I think we have reached the end of our time. But just one thing I wanted to say is that we will be presenting more results and more data this summer at the different conferences. We are trying really to be at all the main conferences in the field. So we will have a workshop at the ISPGR, a workshop at the ECAMPAMP, presentations at the European Society of Biomechanics, World Congress of Biomechanics. So our goal is really to try and keep whoever is interested updated as long as we go. So really thanks to all of our speakers today for a great job they've done. As I mentioned at the beginning, this is the last webinar of this series, but we will now start talking about the following steps of Mobilise, including the clinical validation and further development. So hopefully we'll see more of you in all the coming webinars. And if you are interested, if you have lost the previous seminars, they are available on YouTube. So again, you can find them there. And we have on our website the list of all, we keep updated the list of the papers that we publish and the data that we share. Everything that we produce that can be shared with the community is posted on our website. So please come and have a look if at some point there's something you want to know more about, and come get in touch with us. We're all happy to work with you and to comment further. So thanks again to the speaker and to everyone who attended today, and hope to see you all in person around at the coming conferences. Thanks for all the nice words I'm saying in the chat as well. Bye.